Okay, we have a momentum conservation problem. So let's get started. You slide a 0.02 kilogram magnet, magnet 1, the left one, on a slippery tabletop towards a second 0.03 kilogram magnet, number 2, sitting near the table's edge. As the magnets collide, they're stuck together and they fall off the table. Assume the table to be 0.75 meters tall, and if your magnet was moving at 1.2 meters per second before it collides with the stationary magnet, that's number 2, find how fast they are right after the collision, and also find how fast they will strike the ground with. Okay, so this is a typical combination of a collision problem with an energy conservation problem. You may think it's a collision with a projectile motion problem, but since we're not asked about these typical projectile motion problem questions, such as how long it takes to fall, and also how far off the table's edge, and also the exact direction of the final velocity, these things were not asked. They were only asking for the speed the combined magnets strike the floor, which is a parameter that we can use energy conservation to figure out, just speed, right? So over here I have 3 separate diagrams. So I'll label this with Roman numeral number 1. So this is when this magnet is still kind of moving. Just kind of drawing this is like it's dragging air to make it look like it's moving. But as we know, if it drags air, then there's going to be some reduction of mechanical energy. Anyway, this kind of indicates that the left one's moving to the right, this way. Alright, so the second instance right here, Roman numeral number 2, this is when the air is stuck together right after the collision. They're still moving, but not as fast. Together they're moving off the edge of the table. And this is number 3. We still have the table in sight, but the table is no longer relevant. We're now on the ground, right? So we're kind of moving downward with some sort of a maybe angled velocity. We're coming down like that. Okay, anyway, we're about to hit the floor. We haven't hit the floor yet, so the velocity hasn't been affected or changed by the floor, so it's still falling down. Okay, so now with these 3, recall what we do is we have a list of total mechanical energies, and that list includes mechanical energies for both 1 and 2. Okay, so the total mechanical energy, well, let's see, is kinetic energy 1 plus potential energy 1 plus kinetic energy 2 plus potential energy 2. So we have 4 terms, but let's take a look. The collision here, during the collision, is that total mechanical energy conserved? Well, we know that they are stuck together, so this is called a completely inelastic collision. So the mechanical energy between 1 and 2 is not conserved. So we most likely lose energy. So over here between these two, the mechanical energy is not conserved. What is conserved is momentum. So momentum is conserved. Let's do P1 equals P2, because the collision involves this completely inelastic collision. But between 2 and 3, because the combined magnets just fall off the tabletop and is about to hit the ground, so the mechanical energy is conserved. So we can use E2 equals E3. But at the same time, because the speed keeps increasing, the momentum is no longer conserved. So this is kind of a piecewise momentum conservation between 1 and 2, and then mechanical energy conservation between 2 and 3. Sometimes they are conserved at the same time, other times they're just like this. Sometimes they just one is conserved, the other is not, then there's a switch of the roles. Now the other one gets conserved, this one's not. So that's the total mechanical energy. Let's specify this as kinetic plus potential, because we know it's only conserved between this combined state and the other combined state. So we'll have just combined mass, mass 1 and 2, and velocity squared plus mass 1 and 2, g and y. So the y can be from the ground level and up. Y ground level 0, the tabletop is at a height of 0.75 meters. Okay, so we can just further simplify this into mass total v squared plus mass total g and height. Okay, so momentum. Alright, momentum total. This is only for the collision part, so that's P1 plus P2, or M1V1 plus M2V2. Okay, so now we can use momentum conservation between 1 and 2. P1 Roman numeral equals P2 Roman numeral, and that gives me here M1 V1. This is the initial. 1 is moving toward the 2, but 2 is not moving, so the 0. And then they're stuck together, so they're moving at the same final speed. We can call this a V. Alright, so we're supposed to solve this V. Shouldn't be too hard, we just plug in the values. So the V is equal to M1 V1 over M1 plus M2. So M1 is 0.02 and V1 is 1.2. 0.02 plus 0.03, so we have a 0.05 total. Let's remember that, and you can use your calculator to get this value. And this is supposed to be 0.48 meters per second. Okay, so that's from collision. We can use this as the velocity at 2. So now you separately use energy conservation between 2 and 3. And this is the total energy, so 1/2 mass total. This is that velocity right here. Let's put some subscripts here. Doesn't look good. V2. Okay. Plus M total. Gy2, which is the 0.75, equals 1/2 M total V3 squared plus M total G times 0 height 0. Okay, so that term is gone. Okay, so looking across the equal sign, we have M total, M total, M total. So M total can divide out. So we have 0.5 times this 0.48 squared plus M total is gone, 9.8 times the height is 0.75 meters equals 0.5 V Roman numeral 3 squared. So from here we can solve the V3, which is equal to 0.48 squared plus 9.8 times 0.75 divided by this 0.5 and then square root. Okay, and this gives us 3.86 meters per second. So I know that sometimes you're used to using energy conservation, but because of this collision, right, this collision is inelastic. So stuck together, let's emphasize that this is inelastic. So inelastic, you cannot use energy conservation. Okay, so let's put that in the final note. Alright, thanks.